You probably remember solving exponential and logarithmic equations from your intermediate algebra class or whatever, but I know for some of you guys it's been a while since you did this math, so I did want to review the basics of solving equations. And the way I like to do it is not how everyone does it. There's a couple ways you can do it. But what I like to focus on is what are called the cancellation properties for logs and exponentials, which I talked a little bit about in the previous videos on logarithms. But essentially, since the logarithmic functions are inverse functions to exponentials, there'll always be a cancellation when they're composed together. And this is going back to properties of inverse functions. It's kind of like a square root and a square. They cancel each other out. That's the purpose. Or plus 2 and minus 2, or times 3 and divided by 3. Inverses cancel, logs and exponentials are inverses. And so these properties, which I've put in the little box in the notes, are called the cancellation properties for exponentials and log. But what it says is, if I take log base a of a to the x, meaning I compose log base a and exponential function base a, the log a and the a will cancel each other out, leaving with just x. And again, the reason this works is because they are the same base, and logarithms invert exponentials. Or similarly, if I take a and raise it to the log base a of x, a and log a will also cancel each other out and leave me with just x. And the reason why these cancellation properties are important is because we can use them to help solve equations. Like how I could imagine this is, say I have 3 to the x is equal to 11, and I want to know what's the answer. Well, obviously it's not 2 because 3 squared is 9. It's not 3 because 3 cubed is 27. But it's got to be somewhere between 2 and 3 to make 11. And what is it? Well, it's going to be, technically it's a logarithm, and that's the reason logs exist, is to solve such situations. But actually, let me just erase some of this because it's distracting me. All right, go away. But how could we begin? But essentially, notice that on the left-hand side of this equation, I have 3 to the x. If I was to take the log base 3 of 3 to the x, it would cancel and leave me with only x. And that's the general rule of thumb in algebra, right? If I'm trying to solve the equation, I want to get x by itself. In the question of with an exponentials, how do I get rid of the x? I've seen a lot of students try to divide by 3 or subtract 3 here, but that doesn't make any sense because this is not 3 times x. If it was 3 times x, dividing by 3 would work, but that's not what an exponential means. And subtracting 3 obviously won't work either because that only works for 3 plus or x. So again, the only way to get rid of an exponential base is to apply logarithm base 3. If I apply log base 3 to both sides, and I'll just go ahead and rewrite it like this so I have enough space, but I'll apply log base 3 to the left-hand side of my equation, and I'll apply log base 3 to the right-hand side as well. Log base 3 of 3 to the x will cancel by the cancellation properties. And it's just something that will happen. It will work. And this will leave me with x equal to log base 3 of 11. And then that's literally it. That's my answer. The answer to this equation is log base 3 of 11. And if you remember, my whole spiel about logarithms is to imagine what this means. Log base 3 of 11 always means, well, what power do I need to raise 3 to get to 11? That's exactly what this equation says, right? 3 raised to what is 11? And this logarithm is the solution. It's sort of like a square, like say, imagine the square root of 5. That means, well, what squared makes 5? This is sort of similar. 3 to what power makes 11? I think of logs as being very similar to roots. It's not the same because it doesn't have to do with polynomials. It has to do with exponentials. And of course, we could use either the change of base formula or the log function in a calculator to figure out what this approximates as a decimal. But this would be what we call the exact answer to the equation. Or, we could get an approximated answer as about 2.18. And again, we could check this out. If we take 3 and raise it to the 2.18 whatever power, we see that comes out to being 11, and it makes sense. As with any algebraic equation, the answer, right, x should make sense in the original when you plug it back in. So similarly, looking at the next two examples, the key is To solve an exponential equation, you use a logarithm with the same base. So let's say I wanted to solve 10 to the x plus 3 equals 0.1. Well, I would need to use log base 10, the common log. So if I apply common log to both sides, log base 10 and base 10 will cancel, and this will leave me with x plus 3 is equal to log 0.1, which is negative 1, which you could use a calculator to figure out as well. But that's just because 10 to the negative first power is 0.1. And then I could subtract 3 from both sides to get negative 4 as the answer here. Sometimes you could solve these sorts of equations without a calculator. But, you know, it's not, most people aren't, you know, I teach logs and exponentials all the time, so I'm very familiar with how they work. And again, that's why I'm going to give you some practice problems to work on these. Now, and again, with dealing with e, the natural exponential function, ln is the inverse to e to the x. So if I want to cancel out base e, that's why ln is so important. So if I were to take the natural log of both sides, ln cancels e, again, as we looked at in the previous video, which will leave me with negative 2x is equal to the natural log of 0.0569. And again, I could use a calculator to approximate what that all is. It's going to be approximately, again, I'll change my equal sign to approximately symbol, which is just a good habit to get into, but approximately negative 2.87. And then if I divide that by negative 2, I could solve for x. X is approximately 1.43. Or the exact answer, I could just leave it as the natural log of this divided by negative 2. In the next video, we will look at solving logarithmic equations. It's a very similar approach, but instead of applying the log to both sides, we're going to apply an exponential with a matching base. Key is the base is always the same. Like, how do I know what to do in each of these? I use a logarithm of the same base. With logs, we use an exponential of the same base to cancel.